Okay, second to last lecture of the unit. Test is going to be on March 27th, our last class before spring break. Hopefully I've announced that in class by now, but let's jump into the history of life on Earth. It's a long history, but this video should be fairly short, so let's jump in. Let's give a quick timeline. I apologize, I'm not helping my speed. Quick timeline. So, Earth formed about 4.6 billion years ago. The universe is like 14 billion or something. I don't remember exactly. It changes. We didn't have oceans really until 3.9 billion years ago, and we believe the first life showed up 3.5 billion years ago. And we'll talk kind of more about the experiments that showed us this later. The first organic compounds on Earth, the first molecules of life, essentially, were likely near volcanoes or other hydrothermal deep-sea vents. Some of the organic molecules may have come from space, actually. On meteorites, asteroids, we found, I think, even like nucleic acids on those things that formed from the cosmic rays out in space. But essentially, the first organic compounds needed a high energy source to make them. So it's either cosmic rays in space or the intense heat on Earth. And RNA is believed to be the first genetic material because it more directly gives a use in coding for proteins. DNA is more removed from being useful and likely evolved after as a way to kind of preserve the information that RNA contained. So how do we know any of this? One of the major experiments to know is the Miller-Urey experiment. This is an experiment that basically showed, yes, you can make organic molecules using only inorganic building blocks. So they essentially took the gases in our primitive atmosphere, and I'm trying to get my mouse on the screen, but I can't. Oh, well. In the chamber there on the left, so we got water, methane, hydrogen, and ammonia. And they essentially just ran a big current through it. And then it reacted. They cool it down, and they test what they got out. And they found, yes, they were able to make organic compounds out of just these inorganic building blocks. And so this demonstrated that you can essentially get these organic molecules either on Earth, near the hydrothermal vents, the volcanoes, but also in the solar system for meteorites and comets, which is a little weird to think about. So that kind of proved that, yes, life can start from non-living things. You can have non-living things give rise to the precursors of living things, at least. They don't get to full living things from this experiment. But I'm actually just going to skip this slide because I don't really, well, I'll just talk about it. And so the other reasons how we know all these things are from the fossil record. When we know like when life emerged and things like that. We also look at morphological homology, so structures that are homologous to each other, like the hand-ish bone in humans, whales, bats, all having different purposes. Including vestigial structures, that shows common ancestry that leads us to believe that life had a common origin. Additionally, there are many molecular processes and molecules that are very highly conserved across all organisms. They're basically the same everywhere. Think of like the codons and amino acids. They're the same for everything. Even more evidence. All eukaryotic cells have membrane-bound organelles. All eukaryotic cells have linear chromosomes. All eukaryotic cells have genes with introns. So gives us a big hint that, yes, life does have a common single origin on Earth. How do we know how old fossils are or anything about fossils? We can tell how old the rocks are where the fossil is, especially if it's sedimentary rocks put down in layers. You can just kind of organize the layers, and that tells you how old it is. You can use carbon dating, which just uses radioactive carbon isotopes to see how long ago something was put in the rock, and then also just geographical data. If we know that a lake bed dried up this many years ago, things at the top will be that old. But ultimately, our fossil record is very biased. It is incomplete and will forever be incomplete. There is no changing that. It really only shows us species that existed for a long time, because fossils are kind of hard to make. So if you were a short-lived species, you may not even have made a fossil. You have to be abundant and widespread, so there needs to be a lot of you and everywhere as far as possible. Increase your odds of leaving a fossil. And you need to have hard parts. Generally, when we think of fossils, we think of skeletons, bones. And so if you don't have bones, which there are plenty of things living now that do not, then you don't really leave fossils. You just decompose. So you need some sort of hard part, like a shell of a crustacean, bones, something like that. Otherwise, you do not leave an organism or a fossil behind. So estimates are like 99.9% of all species are forever lost and did not leave any fossils. So we're working with very incomplete data. But even with that, we can still learn a whole lot, such as rates of speciation and extinction. Again, most species that have ever lived are now extinct, 99.9%. Some go extinct because of just general, they were outcompeted, but there have been a few mass extinction events that are usually just the result of a very disruptive global change, like the Ice Age, breakup of Pangea, things like that. Or comets that killed dinosaurs. Not the comet, it's a big asteroid, but regardless. Some huge environmental change can be a natural one. There is belief now that we could be in a new mass extinction event that is entirely human-driven, but the jury's a little out on that. It's hard to tell. But these patterns show us what we believe to be called we call it adaptive radiation, which is what we believe to be essentially a big spreading out and diversification of species from a single common ancestor. It's kind of like thinking of the finches and the Galapagos Islands, where you suddenly have a bunch of open niches in the environment, and so you adaptively radiate, you evolve out and fill all those niches. This can happen because of mass extinction events opening up niches by killing off a bunch of other things. It could be because you have a new feature, like the first fish to walk on land and breathe air. It opened up a bunch of possibilities. Or if you just get access to a new region. So like Alaska and Russia used to be connected by a land bridge, but as sea levels rose, that land bridge disappeared. So things got cut off from each other. But back then, too, you could just walk across the land bridge to get to a new area. So you need to have some new big opportunity for change that makes it very advantageous to diversify and evolve all these new species. Ultimately, there is no endpoint to evolution. Everything is evolving still, or are kind of chilling out. But genomes do still change over time. Mutations still exist, even if they don't have an effect. We are still slowly changing our genetic code. And the fossil record does show continuous change for most organisms that are still alive. Sharks are kind of an exception, but most things have a pretty continuous change. We still see very quick evolution in the form of antibiotic resistance, pesticide resistance, etc., that causes a ton of issues. And we've even seen pathogens evolve to cause new diseases, such as COVID-19. So it's definitely still happening. It will continue to happen forever, but it is not a goal-oriented system. Remember, it can only make slight tweaks to what is already there. If there's nothing there, then evolution can't do a dang thing. The example here is the eye, which will sometimes be used as a counterexample to evolution, saying it's too complex to evolve. But we know how the eye evolved. It evolved from very simple photosensitive cells. we get an eye cup that kind of pinches in, and it starts to become more like the eyeball as we know it. But we can describe the eye from a series of slight tweaks, essentially, to existing forms. Okay, that's history of life on Earth. It's honestly kind of the smallest topic of this whole unit. 7.6 will be a bit of a bigger one. We'll do a fun activity with it in class. And that's all I've got. I just filmed this after the last one, so I'm making it through. Bye.